Good evening, and welcome to Sleepy Story. Tonight, beneath the quiet of the late hours, let us take a journey into one of the most haunting mysteries of the universe. We will travel far beyond the stars, into the silent realms of space where the unseen outweighs the seen. Before we set out, I want to pause and thank you for listening. Your presence here, scattered across time zones and continents, turns this small corner of the night into something luminous. If this is your first time joining, a gentle reminder, subscribing helps keep these calm explorations alive. And to those who return night after night, know that your quiet attention is the gravity that holds this work together. Now, let us begin. Astronomers once believed that galaxies could be explained by the light they cast. Stars and gas were measured, their mass estimated, and the dance of orbits traced. But the deeper they looked, the more unsettling the truth became. Stars at the edges of spiral galaxies moved far too quickly. By the laws of Newton and Einstein, they should have spun out into the dark. Instead, they held steady. The galaxies remained intact, as though clasped by invisible hands. It was not a small discrepancy. It was a fracture in the story of matter itself. If the universe contained only what we could see, stars, gas, dust, the equations would fail. There had to be more, an unseen presence enveloping galaxies and binding them together. In the 1970s, Vera Rubin gave this invisible presence a voice through her meticulous measurements. Her data showed that rotation curves of galaxies remained flat, not declining as expected. Stars far from the galactic center moved at nearly the same speed as those closer in. The only explanation was mass we could not see, mass outweighing all the luminous matter combined. Galaxies, it seemed, were wrapped in enormous halos of the invisible. This discovery reshaped cosmology. What we see, the glowing stars, the shining nebulae, the blazing quasars, is only a fraction of reality. The rest is dark matter. Silent, invisible, and utterly dominant. It does not shine, does not reflect, does not scatter light. It moves through the cosmos like a ghost felt only by its gravity. Picture the Milky Way. To your eyes, it is a glowing river stretched across the night. But the stars you see are suspended within a vast, transparent cocoon, a halo of dark matter many times larger than the luminous disk. Our sun orbits within this invisible sphere, and our Earth, so fragile and small, rides in its current. We live inside dark matter, every second of our existence. Despite its overwhelming presence, it refuses to reveal itself. Scientists search for it in deep underground chambers, where liquid xenon waits for a whisper of collision. They smash protons together in colossal colliders, hoping a shadow particle appears in the wreckage. They study the bending of light around clusters of galaxies, tracing the fingerprints of mass that is not there to be seen. Again and again, the evidence points toward its existence. Galaxy clusters move as though dominated by the invisible. Light arcs into rings and curves, bent by the weight of unseen matter. The cosmic web itself, the great network of galaxies spanning billions of light years, forms only if dark matter provides the scaffolding. Without it, the universe would dissolve into a thin mist of atoms, incapable of building stars or planets. Think of what this means. The fire of every star, the cradle of every planet, the chemistry of every breath, all rest on a foundation that refuses to meet our eyes. The visible universe is but a lantern glowing in the night. Dark matter is the glass that holds it. This paradox lingers like a riddle. How can something so central to existence remain so hidden? Is it a particle waiting in the shadows, smaller than any we have seen? Or is it something stranger, something that challenges our very ideas of matter, space, and gravity? As you lie in the quiet tonight, let that thought drift through you, that the universe you know is only a fraction, that what you cannot see is what truly holds it together. Perhaps the greatest architect is the one who builds without ever being seen. And so the question remains, if the stars are only punctuation marks in a larger sentence, What story is the unseen hand still writing across the sky? Step back far enough, and galaxies stop looking like isolated islands. Instead, they form patterns, delicate and vast, as if strung on invisible threads. Astronomers call this grand structure the cosmic web. It is not a metaphor alone. It is a real network, woven by gravity, stretched across billions of light years, and held in place by the invisible mass that guides it. The story of the web begins with faint ripples in the infant universe. After the Big Bang, matter was spread almost evenly, but not perfectly. Tiny fluctuations in density meant some regions held a little more mass than others. Over time, gravity magnified those differences. Regions slightly heavier grew heavier still, pulling in more matter, deepening their wells. Ordinary matter, atoms of hydrogen and helium, was too easily scattered by light to clump quickly. But dark matter, indifferent to radiation, gathered silently. It pooled into halos and filaments, carving the first scaffolding. When the cosmos cooled, gas slipped into those scaffolds, flowing along invisible valleys like rivers finding their channels. Stars lit in the densest knots, galaxies blossomed at intersections, and clusters grew where filaments crossed. Between them stretched vast voids, immense hollows nearly empty of galaxies, places where gravity had pulled matter away, leaving only the faintest traces of light. Maps drawn from surveys of millions of galaxies reveal this structure vividly. Galaxies line up into walls and chains, arcs that stretch for hundreds of millions of light years. The largest of these structures dwarf imagination, superclusters of galaxies connected by bridges of light, floating on an unseen skeleton. It is as if the universe were an enormous tapestry, its glowing threads embroidered upon a canvas we cannot see. Light itself confirms the web. As it travels from distant galaxies, it bends around concentrations of mass. Sometimes the distortion is dramatic, rings and arcs known as gravitational lensing. More often, it is subtle, tiny stretches in the shapes of background galaxies. By tracing these distortions, astronomers can map the distribution of dark matter directly. The invisible reveals itself not by shining, but by bending the light of what does. Even the spectra of distant quasars whisper of the web. Their light, passing through intergalactic gas, carries scars, thin absorption lines known as the Lyman alpha forest. Each line marks a pocket of gas clinging to a filament, shaped by the unseen gravity beneath it. Piece by piece, these clues form a portrait, a network spanning the entire cosmos, woven from shadows. The web is not static. Matter continues to flow along filaments, feeding clusters at their intersections. Galaxies collide and merge in these crowded nodes, their shapes twisted by encounters, their stars stirred into tidal streams. Meanwhile, the voids expand, pushing matter toward their rims, sharpening the outlines of walls and filaments. The pattern grows more intricate with time, like frost spreading across glass. Simulations confirm this living structure. In vast supercomputers, billions of particles are allowed to evolve under gravity alone. From near-uniform beginnings, filaments emerge, voids deepen, nodes grow dense. When gas and light are added, the simulated universe mirrors the one we observe through telescopes. The web is not an artistic flourish. It is the inevitable outcome of gravity guided by dark matter, and we are part of it. The Milky Way resides inside a filament of the local sheet, a strand of the web stretching across tens of millions of light years. Our galaxy and its neighbors are not drifting randomly. They move along the currents of this network, pulled by dense clusters, nudged by expanding voids, bound into the architecture of the unseen. Think of the scale. A single filament can extend hundreds of millions of light years, containing galaxies by the thousands. The voids between are equally immense, silent expanses where galaxies are rare. The structures are so vast that if the universe were shrunk to the size of Earth, a galaxy would be smaller than a grain of sand, and still the web would span from horizon to horizon. There is something profoundly humbling in this. Our galaxy, our sun, our Earth, all sit not at the center, but on the strand of a vast cosmic spiderweb. We are part of a pattern so immense that even our imagination struggles to contain it. The luminous structures we see are only highlights, glowing beads strung on invisible threads, and still the question presses forward. If the cosmic web is real, if its threads bind galaxies and shape the universe, what are they truly made of? Are they woven from particles that forever escape detection? Or are they signs of laws of gravity not yet understood? The universe shows us the pattern, but not the material. The web is vivid, but the strands remain nameless. Perhaps hidden within those threads lies not only the answer to dark matter, but a clue to something even deeper. A new layer of reality, waiting to be seen. A map of the invisible is not the same as a meeting. We can weigh halos, trace filaments, and watch light bend around mass that refuses to shine, but those are silhouettes cast on a screen. To step closer, scientists have tried something audacious, to catch a single piece of the shadow in their hands. That decision pulled research deep underground, into mountains and abandoned mines, into rooms so quiet a snowflake would sound like thunder. In those caverns, a new kind of astronomy listens inward, not outward, searching the space inside a tank of liquid for a whisper from the Milky Way's dark halo. The idea is deceptively simple. If the galaxy is filled with invisible particles, they should drift through Earth in vast numbers, crossing rock, air, and bone as if none of it mattered. Very rarely, one of those particles might bump an atom in a detector and jostle it. An elastic nudge, a recoil measured as a faint flash of light, or a tiny ripple of charge. Build a vessel clean enough, cold enough, and quiet enough, and a single recoil could be separated from the background hiss of the world. That single sparkle would be a greeting from the unseen. So, laboratories were built where noise cannot easily follow, beneath kilometers of stone, under lakes, inside mountains. Cosmic rays that rain down on the surface are muted there, their chatter hushed by shields of rock and water. Inside the caverns, walls are lined with layers of copper and lead, plastics and ultra-pure materials that will not themselves betray the measurement with stray radioactivity. Every screw, every cable, every seal is chosen for silence. The rooms feel like chapels, full of technology and reverence. At the heart of these sanctuaries stand elegant machines. Many rely on large volumes of liquid xenon or argon, noble elements cooled into clarity. A passing particle that kicks an atomic nucleus sends a tiny flash of scintillation light and frees a handful of electrons. Photomultipliers or silicon sensors watch for those glints, comparing the timing and brightness of signals to tell a true nuclear recoil from an imposter. Electric fields drift freed electrons upward so their second signal can be counted. Two flashes, one prompt, one delayed, become a signature of something that actually struck the liquid instead of brushing an electron cloud or shedding background radiation. The instruments must distinguish signal from everything else the universe throws at them. Neutrons can mimic the sought-after recoil. Radon daughters can cling to surfaces and emit misleading events. Even the materials of the detector can produce traces that have to be accounted for and subtracted. Teams spend months measuring the radioactivity of bolts and gaskets, polishing surfaces, purging air, counting every atom that might pretend to be a message from the halo. There is a monastic patience in these preparations. Each source of noise is named and taught to be quiet. A separate branch of the hunt uses a different sense. If dark matter is not a heavy, sluggish particle that punches nuclei on rare occasion, it might instead be an almost weightless quantum, a field-like ripple that brushes electrons or stirs photons in a resonant cavity. Experiments called haloscopes sit inside strong magnetic fields with exquisitely tuned microwave cavities, scanning frequencies like a radio seeking a station. A whisper of power at the right pitch could betray a particle that never leaves a track, an axion converting into a photon only under the right conditions. The tuning is slow. Frequencies are explored one narrow slice at a time, like combing a beach with a fine-toothed rake. Other searchers cast their gaze upward again, but for a different sort of clue. If invisible particles can annihilate one another or decay, the debris could include familiar messengers, gamma rays, neutrinos, antimatter. Space telescopes and ground-based observatories aim at places where dark matter is dense and ordinary astrophysics is comparatively quiet. Dwarf spheroidal galaxies orbiting the Milky Way, for example. A surplus of high-energy photons from these dark, star-poor systems would be difficult to explain with supernovae or pulsars. The signal would not say everything about the culprit, but it would point with a steady finger. Particle colliders provide a third route, not by catching what passes through us, nor by cataloguing its cosmic leftovers, but by trying to make it. Smash protons together with such ferocity that new particles condense from the energy, and then watch for momentum that goes missing. If something unseen, non-interacting and massive flies out of the wreckage, the debris recoiling in the opposite direction tells you it must have been there. The signature is indirect, a silhouette in the distribution of fragments, but a sudden abundance of silhouettes would be hard to ignore. Add to these efforts the astronomical bookkeeping that looks for consequences too subtle for the unaided eye. Starlight from strongly lensed quasars arrives by multiple paths, and tiny subhalos of dark matter along those paths can shift the brightness ratios between images. Diffuse lensing patterns across the sky carry the statistical imprint of clumps too small to seed a galaxy, but large enough to curve light. Stellar streams, tidal ribbons ripped from dwarf galaxies around the Milky Way, remember every bump and tug. A dark clump that once drifted through leaves a gap and a ripple as a calling card. Even the way satellites of the Milky Way are arranged, and the character of their inner mass profiles, turn into probes of the particle's nature. Colder particles carve sharper cusps. Warmer ones smear the cores. For all this ingenuity, the hunt remains disciplined rather than triumphant. No single event has stood up as the unambiguous announcement the community has prepared for. Instead, each new generation of instruments lowers the limit on how often certain interactions can occur, how strong certain couplings can be. Whole continents of theoretical parameter space have been crossed off with a steady pencil. This cartography might feel like erasure, but it is movement, the way a sculptor reveals form by removing stone that does not belong. It is worth remembering how much has been learned by what has not been seen. Massive compact halo objects, black holes, faint stars, cold clumps of gas were once contenders for the missing mass. Microlensing surveys watched for the brief brightening of background stars as a massive object drifted in front, acting as a tiny lens. The statistics did not add up to what would be required. The scaffolding of the cosmos is not made of familiar dim things hiding in the dark. It behaves like a new kind of matter. The silence underground also speaks with detail. If experiments searching for heavy, weakly interacting particles continue to push down sensitivity without a trace, attention moves toward lighter or more feebly coupled possibilities. Haloscopes increase their reach by widening the band of frequencies or cooling noise closer to the quantum limit. New ideas bloom. Dish antennas that might catch a faint radio glimmer, dielectric stacks that boost conversion, sensors that detect a handful of vibrational quanta in a crystal struck by a minuscule visitor. The toolbox keeps expanding because the mystery refuses a single path. All the while, simulations of structure formation are rerun with alternative assumptions. If the invisible particle is warm enough to smear out the tiniest clumps, there should be fewer dwarf galaxies and cleaner cores in their centers. If it is ultralight, interference patterns can form on kiloparsec scales, changing how stars settle and how central black holes grow. Observers answer in turn, counting satellites, measuring stellar dispersion in dwarfs, mapping the way gas rotates in fragile disks. The conversation between sky and lab becomes the real instrument. There is a human cadence to this work that suits the night. Graduate students spend long, quiet shifts watching stabilizers hold a detector at temperature, balancing liquid levels, whispering to one another so as not to disturb a room that cannot hear them. Postdocs write code that teaches a machine to say no to tricksters and yes to the rare, honest glint. Senior scientists argue gently over systematics on whiteboards, adding arrows and boxes until the scribbles become a plan. A new limit is announced not as a defeat, but as a map update. A fluctuation is investigated and then crossed out with relief when it proves to be a stuck channel rather than a cosmic visitor. Progress is made in careful, audible steps. A bolt tightened, a background halved, a lifetime extended, a blind box opened. Perhaps the most remarkable feature of the hunt is how many domains it threads together. Cosmology provides the mass budget and the large-scale map. Astrophysics supplies targets, contrasts, and the quietest corners to listen. Particle physics offers mechanisms and experimental discipline. Condensed matter physics delivers sensors that can hear a handful of photons or electrons where ordinary instruments would register nothing. Engineering, chemistry, materials science, each adds a silence or a strength the others cannot. The search for an unseen particle makes unlikely neighbors share a hallway, and still, the deeper question glows. Suppose a flash appears that refuses every mundane explanation. Suppose it repeats with a rate and energy spectrum that draw an unmistakable curve across the page. Suppose colliders start to hint at missing momentum in patterns that rhyme with the underground signal. What would belief feel like at that moment? Would the cosmos suddenly become less mysterious, or would a new set of riddles stand up behind the first? Composition is not character. A name for the particle would not by itself explain why the universe chose a scaffold so elegant, or how this invisible component shaped the emergence of life from stardust it held in place. There is also a humbler possibility that the shadows are a choir, not a soloist. The mass we call dark could be a mixture, some portion a heavy shy particle, another portion a light field, perhaps even a faint revision to gravity's grammar joining the ensemble. If this is the score, then no single experiment, however perfect, can play the entire melody. Only the harmony between detectors, telescopes, and theory will reveal the line. The night rewards patience, and the search has learned to move at the night's pace. Sensitivity doubles, then doubles again. Backgrounds are understood in detail, then pared away. New materials and techniques take shape, while older ideas are retired with gratitude. The puzzle no longer feels like a locked door. It feels like a corridor with lights turning on one by one, each revealing a stretch of wall covered in patterns that were always there. Somewhere in that corridor, a first, unmistakable footprint may be waiting. It will be small, smaller than a mote, and short-lived. It will not be a golden plate with an inscription, only a number on a screen, a flash that refuses to be ordinary, a missing momentum vector that points nowhere familiar. But from that fleck of evidence, a story can start to speak. The silhouettes would gain a voice. The web would gain a thread you can touch. Until then, the halo of our galaxy keeps flowing through every stone, every sea, every chest. The detectors keep listening. The sky keeps hinting. The equations keep suggesting what the ears have not heard. And the question grows sharper, not softer. If a single invisible grain crossed a silent tank tonight and left a mark finer than dust, would we recognize the handwriting of the universe? Or would we only learn once more how much the dark can say without a sound? Galaxies are islands of light, swirling whirlpools of stars, gas, and dust. From a distance, their shapes are familiar. Grand spirals with arms curling outward, round ellipticals like smudges of smoke, irregular clumps scattered like broken jewels. Each glows with billions of suns, but beneath the beauty lies a tension. By visible matter alone, these structures should be fragile. Their stars move so quickly that the disks should unravel. Their delicate spirals fly apart, their cores dissolve into scattered streams. And still, galaxies endure. Their shapes remain stable for billions of years, long enough for stars to form, live, and die, long enough for planets to rise from dust, long enough for life to appear and wonder. The secret is an invisible skeleton. Around every galaxy lies a halo of dark matter, massive and extended, reaching far beyond the starlight. These halos provide the gravity that keeps galaxies bound. They are the silent glue, unseen but indispensable, holding galaxies together against their own momentum. Imagine the Milky Way. Its glowing disk stretches about 100,000 light-years across, a flat spiral of hundreds of billions of stars. But the halo surrounding it extends at least 10 times farther, a vast sphere of invisible mass. When astronomers measure the speeds of stars orbiting in the outskirts, they find them racing at hundreds of kilometers per second. Without the halo's gravity, those stars would escape. The disk would shred itself. Instead, the stars remain bound, locked into an elegant orbit that endures across cosmic time. These halos do more than hold, they shape. In simulations, galaxies form only within halos massive enough to capture and cool gas. Small halos struggle. Their gas is blown away by supernova winds or ionized by early radiation. Large halos thrive, feeding a steady stream of cold gas into their centers, igniting generations of star formation. In this way, halos act as regulators. They decide which galaxies become giants and which remain dwarfs, which blaze with starlight and which fade into obscurity. Interactions between halos are equally powerful. When galaxies collide, their halos meet first, overlapping and merging long before the disks touch. The dark matter acts as both cushion and conductor, guiding the dance. Spirals twist into tidal tails, stars fling outward in arcs, and eventually the luminous matter settles into a new form. But the merged halo already embraced both galaxies, dictating the outcome from the beginning. Clusters of galaxies amplify this truth. They are bound not by the light of thousands of galaxies alone, but by immense dark halos enveloping the entire cluster. Gas inside them heats to millions of degrees, glowing in X-rays, but even this hot plasma cannot account for the gravity at work. Only dark matter explains why clusters hold together, why they bend light from background galaxies into giant arcs, why they stand as the universe's most massive structures. Observations confirm this invisible glue again and again. Rotation curves of galaxies, velocity dispersions of clusters, gravitational lensing arcs, all point to halos heavier than all visible matter combined. Without them, the universe would be incoherent, stars scattered like dust in the wind. With them, it becomes structured, resilient, and long-lived. Even the fate of galaxies is tied to these halos. The Milky Way and Andromeda are destined to merge in about 4 billion years. Their disks will collide, their stars flung into tidal streams, their central black holes spiraling together. But their halos are already drifting closer, their invisible edges touching like the outer atmospheres of clouds. Long before the disks meet, the halos will have bound them. The galaxies are already engaged, their marriage written in shadow, and still, questions remain. What is the nature of these halos? Are they smooth, featureless spheres, or are they clumpy, filled with substructures too faint for stars but strong enough to tug? Observations of stellar streams hint at interruptions, gaps where invisible masses once passed through, like fish darting beneath the surface of water. The halos may be crowded with subhalos, dark satellites orbiting unseen, testaments to the scaffolding's fine detail. Galaxies, then, are more than what meets the eye. They are partnerships, light bound by shadow, stars held by silence. Every spiral arm, every glowing bulge, every faint dwarf companion owes its stability to the unseen, and the mystery deepens. If halos hold galaxies, what holds the halos? If dark matter is the glue of the cosmos, what is the glue of dark matter itself? Does it interact only through gravity, drifting forever unbound? Or does it whisper with forces unknown, hidden from our instruments? The answer may decide not only the fate of galaxies, but the fate of the universe itself. If galaxies are islands of light, then galaxy clusters are archipelagos, thousands of suns gathered into thousands of galaxies, bound together in immense seas of gravity. They are the universe's largest gravitationally bound structures, weighing as much as 1,000,000 billion stars. Within them, galaxies orbit like ships in a crowded harbor. Hot plasma glows in X-rays, and light from far beyond bends into arcs. To understand clusters is to peer into the deepest furnaces of structure, where the invisible hand of dark matter leaves unmistakable marks. One of the most striking truths is that clusters should not exist as we see them if luminous matter alone were at play. The galaxies inside move too fast. The hot gas that fills the cluster, 10 times the mass of all its galaxies, should drift away into space. By ordinary mass alone, clusters would not bind so tightly. Their persistence reveals halos of dark matter so immense they dwarf anything familiar. Halos that enfold entire clusters the way a cocoon enfolds an insect. The bullet cluster is the most famous exhibit in this cosmic museum. It is not a single cluster, but two, caught in the act of colliding. Telescopes capture the hot gas from each cluster as it slams together, piling up in the center like clouds crashing in a storm. But gravitational lensing tells a different story. The mass of the system, traced by how it bends background light, is not centered on the gas. It has already moved through, like phantoms, barely slowed by the impact. This separation, matter we see here, mass we infer there, stands as direct evidence that dark matter passes through ordinary matter almost untouched. The lesson is profound. If gravity alone were modified, without any unseen component, the lensing and the gas would not part ways. The bullet cluster and other merging clusters insist. There is matter we cannot see, moving on its own, revealing itself only through gravity. Beyond collisions, clusters are laboratories of balance. Their hot gas glows in X-rays at temperatures of millions of degrees, held in place not by the galaxies, but by the invisible mass surrounding them. Without dark matter halos, this gas would escape. With them, it remains bound, compressing, cooling in filaments, sometimes feeding starbursts in central galaxies. The interplay between the visible and the invisible sculpts the life of clusters. Clusters also serve as gravitational lenses on the grandest scale. When light from galaxies billions of light years farther away passes through a cluster, it bends around the mass, forming stretched arcs, doubled images, and glowing rings. These cosmic mirages magnify what would otherwise be too faint to see, turning clusters into natural telescopes. They also reveal the distribution of mass inside the cluster. By comparing the locations of arcs with the visible matter, astronomers map the invisible with remarkable precision. Every lensing map confirms the same. The majority of the mass is dark, concentrated in halos larger than the light they surround. Even in simulations, clusters emerge as arenas of drama. Dark matter halos form first, their gravity pulling gas inward. The gas shocks, heats, and glows. Galaxies fall into clusters, their stars stirred, their gas stripped by the hot medium, their shapes transformed. Halos merge into larger halos, creating sprawling complexes where dark matter provides the scaffolding, and the galaxies play only as tracers. In these simulations, the pattern looks eerily like the real sky. Knots of mass colliding, gas offset from halos, arcs bending across backgrounds. The invisible is not just a hypothesis, it is the structure itself, but mysteries remain. If dark matter sails through collisions so effortlessly, does it interact with itself at all? Could there be a faint self-interaction, subtle enough to escape the bullet cluster's clarity, but real enough to leave fingerprints elsewhere? Observations of other clusters hint at possibilities. Offsets between galaxies and halos in some systems suggest there may be more complexity than we know. Perhaps dark matter particles can collide, exchange energy, or form structures we cannot yet imagine. Consider too the voids between clusters. These vast gaps stretch for hundreds of millions of light years, where few galaxies dwell. Are they empty, or do they contain filaments of dark matter, too diffuse for stars, but still part of the web's frame? Lensing surveys continue to probe these expanses, teasing out faint signatures, trying to answer whether the unseen extends even where light dares not tread. The bullet cluster is not alone. Other merging clusters, El Gordo, Max J0025, Able 2744, repeat the lesson. Light and mass separate. Visible and invisible refuse to coincide. The conclusion grows firmer with each example. The universe's largest battles are fought by matter we cannot see. And what of us? Watching these silent collisions from billions of light years away, we see galaxies colliding like sparks in a fire, gas clouds slamming together with ferocity, but the true combatants are shadows. Dark matter streams through the chaos, barely pausing, unbound by heat or friction. It is a reminder that the greatest structures in the universe are sculpted not by what shines, but by what refuses to be seen. As you rest under the stars tonight, hold this image. Two clusters colliding in silence, their gas crashing, their galaxies scattering, their halos ghosting through each other as if nothing stood in their way. If matter so immense can meet without a sound, without slowing, without revealing itself, then what does that say about the true fabric of the cosmos? Could it be that the universe we know is only the faintest trace upon a deeper, invisible sea? The story of dark matter does not begin with galaxies or clusters. It begins in a universe still shrouded in fire, a cosmos so young that stars were unthinkable, galaxies unformed, and light itself trapped in a dense fog of particles. In that newborn storm, ordinary matter and radiation danced together, colliding, scattering, and pushing one another apart. But dark matter stood apart. It did not scatter, did not shine, did not care for radiation's grip. While the visible universe was tangled in light, the invisible began to draw the first maps of structure. Only a few 100,000 years after the Big Bang, the universe cooled enough for atoms to form. Electrons bound to protons, and light was suddenly free to travel. That first light still washes across the cosmos as the cosmic microwave background. In its delicate ripples, astronomers read the fingerprints of dark matter. For even then, invisible halos were pulling matter into wells of gravity, faint outlines of the cosmic web sketched before galaxies were born. Dark matter's role was subtle but decisive. Ordinary matter, tethered to radiation, could not collapse quickly. It needed anchors, places where gravity was already strong. Dark matter provided those anchors. It clumped where density was slightly higher, forming invisible valleys across the young universe. When light broke free and matter cooled, gas flowed into those valleys. Without them, the universe would have remained diffuse, a glowing mist with no sparks of starlight. Hundreds of millions of years passed before the first stars ignited, colossal and brief, many times the mass of our sun. Their light pierced the cosmic dark, marking the dawn of structure. These stars forged the first heavy elements, scattering carbon, oxygen, and iron into the void when they died. But their very existence depended on dark matter. Without its halos, hydrogen and helium would never have gathered closely enough to burn. Imagine the silence of that epoch. The universe was vast, expanding, cooling, but still empty of galaxies. In the darkness, halos grew quietly, deepening, connecting into filaments. Into those unseen arms, gas streamed, pooling in knots where the first stars would blaze. Though no one was there to see it, the architecture was already being laid, the scaffolding of everything to come. Even today, astronomers glimpse these beginnings. The faint ripples in the microwave background, mapped by satellites, tell us how much dark matter was present, how it seeded the first structures. Computer simulations bring the past to life. From uniform beginnings, filaments stretch, voids open, halos gather gas, and the first sparks appear. The pattern repeats no matter how many times the simulation is run. The invisible hand leaves the same mark. But mysteries deepen the closer we look. Did dark matter merely guide structure, or did it interact in ways we have not seen? Could it form its own intricate patterns, too fine or too faint for light to trace? Are the first stars we imagine only a fragment of what once was, their kin hidden or erased by the passage of time? The echoes of that dawn remain with us. Every atom of your body was once scattered by a massive star, born in a halo drawn by the invisible. The carbon in your breath, the iron in your blood, the oxygen in your lungs, all forged in furnaces that would never have burned without dark matter's embrace. You are a child not only of stars, but of shadows, and so the thought lingers, patient and profound. If the first light of the universe was lit by hands we cannot see, then what other fires might those hands still cradle, hidden beyond our reach, waiting to be discovered? Long before galaxies spun their spirals, before clusters gathered their crowns of light, the universe glowed as a furnace. It was a time when matter and radiation were bound in a dense fog, when every particle of light was scattered almost immediately by electrons and protons. The cosmos was brilliant but opaque, as though wrapped in a glowing shroud. Then, after roughly 380,000 years of expansion and cooling, a transformation occurred. Atoms formed, light decoupled from matter, and photons were free to travel across space. That light still exists, stretched into microwaves by billions of years of cosmic growth. It is the oldest light we can see, and it fills the sky in every direction. The cosmic microwave background. To human eyes, the night between stars looks black. But to sensitive instruments, the whole sky glows faintly with this ancient afterglow. And within that glow are ripples, variations in temperature no greater than 1 part in 100,000. Tiny, delicate, but meaningful. These ripples are the fossils of structure. They show where matter was denser, where gravity was stronger, where dark matter had already begun to gather the threads of the cosmic web. Think of it as a photograph of the universe in infancy. In the mottled pattern of the microwave sky, astronomers read the blueprint of galaxies not yet born. The faint hot and cold spots are not random. They are the imprints of dark matter's gravity, anchoring matter even in those earliest times. Satellites have mapped this glow with exquisite precision. COBE first revealed its faint ripples in the 1990s. WMAP sharpened the image, turning static into a portrait. And the Planck satellite traced the afterglow with such detail that cosmologists could measure the age, composition, and curvature of the universe. What they saw confirmed the story. Dark matter was already there, outweighing ordinary matter, guiding the cosmos from its earliest breath. Each ripple in the microwave background is like a note in a cosmic symphony. Together they form harmonics, acoustic peaks, arising from sound waves that rippled through the hot plasma before atoms formed. These peaks tell us the ratio of ordinary matter to dark matter, the density of the universe, and the seeds of structure. Without dark matter's extra gravity, those sound waves would not have the right rhythm, the ripples would not have the right shape, and the universe today would not hold the galaxies we see. Even the smallest variations are significant. Regions where dark matter had gathered slightly more deeply became the birthplaces of filaments and clusters. Regions where it was shallower became the voids. The entire skeleton of the cosmos was already written in those faint ripples. Astronomers sometimes describe this glow as the baby picture of the universe. But it is more than that. It is a memory, a relic of when light and matter parted ways, carrying with it the whispers of the unseen. And in those whispers, we find proof that the invisible outweighs the visible 5-1. The afterglow is not silent in practice. A detuned television, an untuned radio, both carry fragments of it in their static hiss. Even in our technology, even in the hum of abandoned frequencies, the birth cry of the cosmos echoes. We are surrounded every day by the residue of creation, and still, questions remain. The cosmic microwave background is precise, elegant, almost too clean. Could there be anomalies within it that hint at deeper truths? The so-called cold spot in the southern sky defies easy explanation. Too large, too deep, too strange. Is it a statistical fluke or a sign of new physics? Perhaps even an echo of other universes brushing against our own? The afterglow is both answer and riddle. It proves dark matter's role, but it also raises mysteries we cannot solve. It tells us the universe was shaped by shadows, but it also hints at possibilities beyond those shadows. As you drift into sleep tonight, Imagine the whole sky glowing faintly with the memory of creation, the first light stretched thin by time. Every ripple is a fingerprint of the unseen. And perhaps the deeper mystery is this: if the universe remembers its birth so clearly, what other secrets might be written in light we have not yet learned to read? The grand structures of the universe often steal our imagination. Galaxy clusters colliding, filaments stretching across billions of light years, light bent into arcs by unseen mass. But sometimes, the deepest secrets are whispered by the smallest voices. Among the faintest and most fragile of galaxies lie clues that could decide the very nature of the cosmos. These are the dwarf galaxies, dim companions to giants like our Milky Way, places where dark matter does not just accompany the story, it dominates it. If the Milky Way is a great lantern glowing in the night, dwarfs are its tiny sparks, almost invisible, and yet they carry disproportionate weight in the search for truth. To an untrained eye, they look unremarkable, clouds of a few million or a few billion stars at most, scattered across space like crumbs around a feast. Some are spheroidal, their shapes soft and faded. Others are irregular, ragged from tidal forces, their gas long since stripped away. But their modest glow hides an overwhelming presence. Astronomers tracing the motions of stars inside these dwarfs find a paradox. The visible stars cannot explain the gravity holding them together. In many of these galaxies, dark matter outweighs the stars by factors of hundreds. In such places, the invisible is not a supporting character, but the main stage. From this stage, rise puzzles that unsettle the neat models of cosmology. Simulations of cold, collisionless dark matter predict that halos should grow sharp cusps at their centers, steep rises in density like a mountain peak. But when astronomers measure dwarf galaxies, many appear to have soft cores instead, as if the peaks have been flattened into plateaus. One explanation invokes the fiery temper of ordinary matter. As bursts of star formation flare and die, supernovae hurl gas outward, the gravity shifts and dark matter orbits are stirred, smoothing the central spike into something gentler. Another possibility is more exotic, that dark matter itself is not entirely aloof, but collides softly with its own kind, exchanging just enough energy to flatten its inner profile. Each dwarf becomes a courtroom where these explanations compete, their motions a testimony written in faint starlight. Another puzzle appears when we count. Simulations of a Milky Way-sized halo predict hundreds of sub-halos orbiting like sparks around a flame. Early surveys found far fewer luminous satellites than expected, giving rise to the missing satellites dilemma. But the story is subtler than absence. The faintest dwarfs are nearly impossible to detect, hiding in the foreground stars of our own galaxy. As telescopes probed deeper, more companions were found, some with only a few thousand stars, fragile systems barely holding together. And even more importantly, not every halo should shine. When the universe reionized, the flood of starlight heated gas so thoroughly that the smallest halos could never gather fuel again. They remain dark to this day, empty lanterns drifting unseen. Count only the halos massive enough to light a flame, and the mismatch softens, but it does not vanish entirely. Then, there is the riddle of the satellites that do exist. The brightest dwarfs orbiting the Milky Way seem less dense than the most massive subhalos in simulations. Those predicted halos should have been too big to fail at forming stars, yet our satellites appear lighter in their hearts. Once again, the answer may lie in the interplay of forces. Tidal stripping by the Milky Way can shave away mass, making the satellites gentler than their ancestors. Early starbursts and supernova winds may have softened their cores. The Milky Way's history, its mergers, its growth, its tides, may have sculpted the satellites into what we see. None of these explanations exclude the others. Each adds brushstrokes to a portrait that is still unfinished. As observations grow sharper, even stranger whispers appear. Some analyses suggest that the satellites of the Milky Way and Andromeda are not scattered randomly, but lie in thin planes, like beads threaded on invisible strings. Whether this alignment is rare or illusory is debated, but the suggestion itself deepens the intrigue. If real, such patterns could hint at subtleties in the way halos gather companions or in the physics of the unseen. Beyond satellites, the tidal streams of stars ripped from past mergers record scars of encounters with dark subhalos. When an unseen clump drifts through a stellar stream, it carves a gap, a ripple, a memory written in the sky. Streams become seismographs of the invisible, tracing tremors we cannot otherwise see. Even light from far quasars adds to this chorus. When a galaxy lenses a distant quasar into multiple images, small dark clumps along the line of sight can change the brightness ratios between those images. These flux ratio anomalies reveal subhalos too faint to shine, but too heavy to hide their presence. Across dozens of such lenses, a statistical portrait emerges. The universe is crowded with dark structures we cannot see. Each of these puzzles invites interpretations that touch the very essence of dark matter. If it is cold and collisionless, then baryons, ordinary gas and stars, must be the sculptors of every core, every gap, every softened profile. If it is warm, then its primordial speed smoothed away the smallest halos long ago, reducing the crowd of satellites. If it is ultralight, behaving more like a wave than a particle, then interference patterns could carve soliton-like cores in dwarfs, changing the music of their motions. If it collides with itself softly, then density peaks would relax naturally into plateaus. Each hypothesis paints a different universe, and the dwarfs, modest as they seem, hold the power to confirm or deny them. The lesson is not just technical, but poetic. The smallest galaxies, the faintest satellites, the fragile streams, these are the places where the universe reveals its handwriting. They remind us that the truth of the cosmos is not only found in clusters blazing across hundreds of millions of light years, but in systems so dim they can vanish into the night sky without notice. A dwarf galaxy is like a whisper in the symphony, quiet but decisive, telling us what the louder instruments cannot. Surveys across the world now push deeper, uncovering dwarfs of astonishing faintness, some with fewer stars than a single globular cluster, held together by halos of invisible mass. Stellar streams are mapped with such precision that their wiggles become legible sentences. Gravitational lenses pile up, each anomaly a syllable in the language of substructure. Piece by piece, the smallest shadows refine the grand narrative, teaching us whether the unseen is cold, warm, fuzzy, or something stranger still. And so, as you drift into quiet tonight, picture these faint galaxies, tiny clouds of stars bound by enormous halos, drifting companions to giants, their fragility masking their importance. Think of the streams etched across the sky, carrying scars of invisible travelers. Imagine halos too dark to ever shine, orbiting like ghosts, leaving only ripples as proof of their passage. Then, let one question linger. If the universe hides its greatest truths, not in its grandest spectacles, but in its smallest whispers, which faint trace will be the one that finally tells us what everything is made of? Every galaxy has a heart. Sometimes that heart is calm, a dense cluster of stars gathered tightly at the center. Sometimes it is ferocious, a supermassive black hole devouring gas, lighting up the galaxy's core with jets and radiation. Whatever its mood, the heart of a galaxy is inseparable from the invisible embrace that surrounds it. The dark matter halo and the central black hole are partners in a story as old as galaxies themselves, bound together by gravity, growth, and silence. The connection begins with formation. Galaxies are born within dark matter halos, vast, unseen cocoons that gather gas and allow it to cool. Without halos, the gas would never settle enough to form stars. But once stars ignite, the center becomes a stage for something even stranger. Black holes, tiny seeds compared to the galaxy as a whole, begin to grow. Some may form from the collapse of massive stars, others from more exotic beginnings in the early universe. However they arise, these seeds do not remain small. Fed by the rivers of gas funneled by the halo, they grow into giants millions or billions of times the sun's mass. Observations reveal a tight relationship between the size of a galaxy's central bulge and the mass of its black hole. The bigger the bulge, the bigger the hole. It is as though the galaxy and its dark partner evolved in step, one influencing the other. But how does this synchrony emerge? Dark matter provides the environment, guiding how gas flows, how stars form, and how material sinks inward. The halo is the stage, the galaxy is the play, and the black hole is the actor who both follows the script and occasionally rewrites it. When black holes feed, they transform galaxies. As gas falls inward, it heats, radiates, and can drive powerful winds outward. Jets launched at near the speed of light pierce the halo, stirring and heating the gas around them. These outflows can quench star formation by blowing gas away, or they can compress gas in certain regions, triggering bursts of new stars. The halo, in turn, determines how these effects spread. A massive halo can hold on to heated gas, recycling it later, while a smaller halo may lose it forever. The dance between halo and black hole is both delicate and decisive. Clusters of galaxies provide dramatic theatres for this relationship. At their centres, supermassive black holes in giant elliptical galaxies drive jets that carve cavities in the hot plasma filling the cluster. These cavities, seen in X-rays, stretch for tens of thousands of light years, like bubbles blown into the halo's heart. They remind us that even the most invisible structures are not static. Dark matter halos may not shine, but they host engines whose power rivals that of whole galaxies, sculpting the very medium they inhabit. Simulations confirm how deeply entwined the two are. When models include only dark matter and stars, galaxies form too many stars too quickly. They shine too brightly compared to real galaxies. But when feedback from central black holes is added, the match improves. The invisible halo guides growth, the black hole regulates it, and together they create galaxies that resemble the ones we see through telescopes. Without halos, black holes would starve. Without black holes, galaxies would grow unchecked. Balance lies in partnership. Still, questions remain as haunting as the silence between stars. Do halos guide black holes only through gravity? Or is there a deeper link, perhaps a shared origin in the earliest moments of the cosmos? Some theories suggest that dark matter itself could collapse under rare conditions to form black hole-like objects. If so, then some of the seeds of today's giants may not come from stars at all, but from the shadows themselves. Could dark matter and black holes be more than partners? Could they be kin? Even the behavior of galaxies on the smallest scales deepens the mystery. Dwarf galaxies, often dominated by dark matter, sometimes harbor black holes in their modest centers. How did such giants find their way into such fragile systems? Did halos guide their formation? Or did black holes emerge first, helping to anchor the galaxies around them? The hierarchy is unclear, as if the cosmos has hidden the order of its story, letting us guess whether halos write black holes into being, or black holes call halos into service. And what of us, sitting in the quiet suburbs of the Milky Way? At our center lies Sagittarius A, a supermassive black hole 4 million times the mass of the Sun, surrounded by a halo hundreds of thousands of light years across. Both are invisible to ordinary eyes, both dominate in ways we do not feel day to day, and both shaped the galaxy that made us possible. Stars circle the black hole like dancers around a silent conductor. Our spiral arms trace the gravity of a halo no one can see. To exist at all is to live in the embrace of two partners we can neither touch nor fully comprehend. As you listen in the stillness tonight, picture the universe not as isolated pieces, but as a symphony of hidden duets, halos and galaxies, black holes and stars, matter and silence. Think of the invisible cocoons that cradle galaxies and the voracious hearts that burn at their centers. And let one question keep you company as you drift. If halos and black holes are locked together in such precise harmony, What deeper score is being played? And who, if anyone, is the composer of this cosmic duet? Galaxies are the ornaments of the universe, luminous collections of stars that trace the outlines of the cosmic web. They dazzle us with spirals and halos of light, with starbursts and quasars, with delicate arms and ancient bulges. But the story of their birth is one of hidden symphonies, a music conducted by players we cannot see. For behind every galaxy lies an unseen framework of dark matter, a silent score guiding when the notes of starlight should rise and when they should fall. In the beginning, the stage was almost empty. The universe was smooth, a fog of hydrogen and helium with only faint ripples of density. Left alone, these gases would never have gathered quickly enough to form galaxies. Radiation pressure from the young cosmos was too strong, the expansion too rapid, the matter too thin. What changed the rhythm was the invisible. Dark matter, indifferent to light, began collapsing earlier, collecting into halos, while ordinary gas was still adrift. These halos were like hidden bowls carved into the expanding universe. Into them, ordinary matter poured, cooling and condensing, finding the gravitational wells already prepared. Without these bowls, there would have been no galaxies, no stars, no worlds. Once gas found its way into the halos, it began to shine. Stars formed, burned, and died, enriching the environment with heavy elements. Supernovae stirred the gas, driving some outward, seeding the intergalactic medium. Black holes grew, their influence stretching outward. But all of this drama played against the silent framework of dark matter. The halos determined the stage, how much gas could be captured, how quickly stars could form, how bright the galaxy could become. They were not just containers, they were the conductors, dictating tempo and tone. Different halos told different symphonies. In small halos, gas was easily stripped or blown away. Their galaxies remained faint, fragile dwarfs that struggled to sustain star formation. In massive halos, gas cooled steadily and collapsed toward the center, giving birth to giants that burned brightly and for long periods. Some halos grew so massive that their gas heated to millions of degrees, glowing in X-rays, making cooling more difficult. These galaxies often grew slowly, with bursts of activity punctuating long pauses. Across the universe, diversity in galaxies traces back to diversity in halos, a hidden harmony that explains why the night sky contains so many forms. Interactions between halos added new layers to the music. When halos merged, their galaxies collided, stars thrown into streams, gas compressed into new bursts of creation. The black holes at their centers spiraled closer, eventually coalescing, but the halos always merged first, their invisible embrace binding the galaxies long before their disks touched. Even the most violent collisions followed a script drafted by the unseen. Astronomers trace this hidden symphony in careful ways. They measure the faint motions of stars in dwarfs, the curves of galaxy rotation, the arcs of lensing across clusters. They run vast simulations, feeding in the laws of gravity and the properties of dark matter, and watch galaxies blossom within. Halos. These simulations show universes filled with spirals and ellipticals that resemble our own. But when they are run without dark matter, the music falls flat. Stars form too late, galaxies collapse too slowly, and the richness of structure vanishes. It is like hearing only a few scattered notes instead of a full orchestra. Still, the composition is not finished. Some galaxies surprise us with too many stars for their halos. Others have too few. Some halos host giants, while others, by all accounts similar, cradle only faint dwarfs. The scatter in the relationship between halo mass and galaxy brightness is like variations in the same score, improvised flourishes we do not yet understand. Feedback from stars, winds from black holes, cosmic environment, and perhaps even new properties of dark matter all contribute to the variations. The music is harmonious, but never monotonous. Consider the Milky Way, our spiral arms, our glowing bulge, our serene outskirts. all of it rests within an invisible halo. The halo decided how gas fell inward, how stars were born, how clusters merged, how satellites gathered. The fact that we live in a galaxy with stable arms, long-lived star formation, and a quiet center is not an accident. It is the result of the halo's hidden hand, shaping conditions across billions of years. Even our sun, even the Earth exists because of this silent accompaniment. And so galaxies are not only collections of stars, they are duets of light and shadow. The visible plays the melody, but the invisible provides the rhythm, the structure, the gravity that keeps the song coherent. Without dark matter, the notes would scatter, the stars would disperse, the music would dissolve into silence. With it, the cosmos sings. Still, the question lingers. If the halos conduct the hidden symphony of galaxies, then what composes the halos themselves? Are they the work of simple, cold particles whispering only through gravity? Or is there a deeper harmony we have not yet heard? If galaxies are the instruments and halos the scores, then who or what is writing the music of the universe? The universe bends. Light, which we imagine as the straightest thing in existence, does not always travel in straight lines. When it passes near something massive, it curves, following the folds of space-time. This bending is not just a curiosity, it is a revelation. For in the arcs and distortions of distant galaxies, we can trace the fingerprints of something we cannot see. Gravitational lensing, the ghost imprint of mass upon light, is one of the most powerful tools we have for uncovering the presence of dark matter. The concept is elegant. A massive object, such as a galaxy or a cluster of galaxies, warps the fabric of space-time around it. Light from an even more distant object traveling toward us follows those curves. The result can be dramatic. Multiple images of the same galaxy appearing in the sky, luminous arcs stretched into crescents, even complete rings known as Einstein rings. But it can also be subtle, with faint elongations or distortions across thousands of background galaxies. Whether dramatic or delicate, the story is the same. Light tells us where mass is, not just where stars are. This is crucial because stars and gas make up only a fraction of a galaxy's mass. The rest, the vast majority, is hidden. When astronomers map clusters using lensing, they find halos of mass far greater than the visible light would suggest. Sometimes the mass peaks are displaced from the luminous matter, as in the Bullet cluster, where colliding halos drifted past one another while their hot gas slammed together. The separation is like a whispered truth. There is matter here that refuses to shine, but it bends light nonetheless. Even weak lensing, the faint statistical distortion of many background galaxies, reveals the invisible. By stacking thousands of images, astronomers measure tiny shears that accumulate across the sky. These shears trace the web of dark matter on cosmic scales, mapping filaments and voids with precision. The result is a ghostly skeleton superimposed on the universe, a scaffold that exists regardless of whether any starlight falls upon it. Strong lensing adds further detail. A single cluster can act as a magnifying glass, boosting the light of galaxies far behind it. Arcs and rings are not only beautiful, but informative. They require precise distributions of mass to exist. By modeling the positions and shapes of these arcs, astronomers reconstruct the underlying mass map. Again and again, these reconstructions show that most of the mass is dark. In some cases, small subhalos, too faint to host stars, are revealed through their influence on lensed images. Dark matter, invisible on its own, betrays itself through the bending of another's light. Even quasars serve as messengers. When a foreground galaxy lenses a distant quasar into multiple images, astronomers watch carefully. The brightness of each image should follow predictable ratios, but often it does not. These flux ratio anomalies point to dark substructures in the lens, small halos invisible to light but heavy enough to tip the scales. Collecting these anomalies across many systems paints a statistical portrait of the abundance of small halos, and the portrait matches what cold dark matter predicts. Gravitational lensing has become not only a probe of where dark matter is, but of what it might be. If dark matter were warm instead of cold, the smallest halos would not exist in such numbers. Lensing statistics would differ, arcs would shift, anomalies would vanish. If dark matter were fuzzy, behaving more like a wave, interference patterns might alter the distribution of mass within halos, changing the way light bends. Each image of a distant galaxy, distorted or magnified, carries within it subtle clues about the nature of the unseen. There is poetry in this. We do not see dark matter directly, but we see how it changes the path of light. We do not hear its voice, but we hear the echo in the notes of background galaxies stretched and reshaped. It is like tracing the presence of wind by watching grass ripple, or sensing the depth of an ocean by the way waves break upon a shore. The universe whispers through distortions, and astronomers listen with patient eyes. And still, the mystery deepens. Lensing shows us where the mass is, but not what it is. We can draw ghost maps of halos, trace filaments across billions of light years, and count substructures too faint to glow, but the substance itself remains hidden. Is it a new particle waiting in the shadows, or a revision of gravity's laws? Are we looking at fingerprints without ever seeing the hand? The sky itself becomes a lens, bending light into arcs and rings, each curve a silent reminder that something unseen shapes the universe. And so the question remains, if light is bent by ghosts we cannot see, what other secrets lie hidden in the silent fabric of space? Across the largest scales, the universe does not resemble a smooth canvas sprinkled with stars. It looks more like foam, filaments and walls forming a delicate lattice, with enormous hollows between them. Those hollows are cosmic voids, regions, so underdense that a traveler could cross for tens, even hundreds, of millions of light years without meeting a single bright galaxy. The eye is easily drawn to luminous cities at the nodes of the web, to clusters where light is abundant, and gravity is strong, but the voids claim most of the volume. They are the true expanse, the silent ocean in which the archipelago of galaxies floats. A void is not emptiness, only relative absence. Within it, atoms drift, faint dwarf galaxies flicker, and dark matter spreads thinly like a mist. Because gravity works by differences. The low density inside a void means that its boundary behaves like a shoreline. Matter outside pulls harder than matter inside, so the interior expands faster than the average universe. Over time, the underdensity deepens. Voids push their walls outward and sharpen their rims, while the web's filaments crowd together like currents converging along the edges of a whirlpool. Seen in simulation, the growth is hypnotic. Caverns dilate, filaments tighten, and the pattern of foam becomes more distinct with age. Dark matter guides this evolution from the beginning. In the young cosmos, tiny variations in density were sculpted by the invisible component more than anything else. Regions that started slightly lighter in dark matter became the seeds of voids. As halos coalesced along filaments, these lighter regions were drained and the difference amplified. Ordinary matter followed the contours already carved, leaving the interior star-poor. Voids are therefore not accidents left over when galaxies were placed elsewhere. They are deliberate features of the invisible scaffold, places where the unseen chose to be spare so that structure could be bold next door. Galaxies that grow inside these hollows carry the imprint of their upbringing. With few neighbors to harass them, they avoid the rough encounters common in crowded environments. Their gas reservoirs remain generous, their disks stay delicate, and their chemistry often preserves a certain youthfulness. Lower metallicities, extended hydrogen envelopes, star formation proceeding in quiet pulses instead of violent bursts. The cosmic ocean breeds patient sailors. Even their shapes, thin, blue, loosely wound, speak of a life with gentle tides rather than storms. Voids also act as lenses of a different sort. They have less mass than average, so instead of converging light, they deconverge it, producing a faint anti-lensing signature. Detecting that signal is difficult because a single void is subtle, but stacks of many voids reveal a consistent pattern. Background galaxies appear, on average, minutely magnified in the negative sense and ever so slightly stretched. These whispers confirm that underdensities are as real as overdensities in shaping how light reaches us, and that the invisible hand arranges not only where mass gathers, but where it refrains from gathering. Because voids expand a little faster than their surroundings, they respond sensitively to whatever drives cosmic acceleration. If dark energy governs the late-time growth of the universe, then voids feel its influence in a way dense regions do not. Their boundaries move, their shapes relax, and their statistics change with time. Astronomers use this sensitivity as a probe, measure the sizes and shapes of many voids across cosmic history, and you obtain a ruler and a clock, a way to test how space stretches and how gravitational potentials evolve. Even the subtle imprint on the oldest light, the integrated Sachs-Wolf effect, where the decay of potentials leaves a trace on the microwave background, can be enhanced along lines of sight passing through large underdensities. If clusters are cymbals in the percussion section of the universe's orchestra, voids are the hush that makes the cymbals ring. The boundaries of voids are not smooth. Filaments braid around them, walls buckle and pinch, tunnels connect hollows, like underwater caves. A galaxy might drift along a filament, slip across a saddle point, and find itself at the edge of another cavern altogether. The topology resembles a network of basins and passes, and the invisible component decides which paths remain open and which collapse. In this geography, dark matter is cartographer and contractor. It sketches the map and also builds the roads. On small scales, the story becomes delicate. If the unseen consists of cold, sluggish particles, then void interiors retain a fine lace of tiny halos, so light that many host no stars at all. Those halos are like micro-eddies in a calm bay, present, structured, but not strong enough to break the surface. If the unseen carries a touch of primordial speed, smoothing the smallest clumps, the void interior becomes cleaner, its lace reduced, its micro-eddies absent. Measurements that count the faintest dwarfs, trace the faintest wiggles in background, galaxy shapes, or red slight patterns in quasar absorption lines can therefore translate emptiness into evidence. A difference in shadow density inside a place with almost no light becomes the deciding vote in a debate about the identity of matter itself. Voids influence motion as much as they shape light. Galaxies near a void's rim feel a gentle push outward, a cumulative effect of less pull behind them and more pull ahead. These peculiar velocities rearrange our maps in redshift space, stretching voids along the line of sight in a way that can be measured statistically. From those stretches, astronomers extract the growth rate of structure, a quantity that answers whether gravity behaves exactly as Einstein described, or whether the cosmic fabric contains surprises at scale. In this sense, hollows teach us how the entire score is conducted, not just where the loud instruments stand. Even anomalies acquire a new context when the ocean is considered. The microwave background contains a famously cold patch whose origin remains debated. Some studies point to an extended underdensity along that direction, a supervoid large enough to leave a faint, integrated fingerprint on ancient light. Whether that explanation suffices is not the point here. Rather, the debate shows how empty space can influence what we read in the earliest photograph of the universe. Absence leaves marks. Human intuition often treats emptiness as neutral, a stage on which actors stride. Voids correct that intuition. The stage tilts, the exits widen or narrow, and the script changes depending on how hollow the set is. Even our local group moves under the combined influence of nearby masses and surrounding emptiness. Attractions tug from ahead, while the vast local void behind adds a subtle push. Motion is the sum of thrust and vacuum. There is also a softer perspective, one that belongs to nights like this. The mind moves easily to bright things, to star clusters and nebulae, to spirals adorned with blue knots of newborn suns. But the form of those beauties was mandated by where the voids stood aside. The negative space is not afterthought, it is composition. A sculptor who carves marble must remove stone for a face to emerge. The universe removes mass for the web to gleam. In that sense, dark matter's most eloquent act may be its restraint, knowing where not to gather so that gathering elsewhere can become spectacular. Imagine a galaxy born in deep solitude. No nearby giants to bully it, no cluster winds to strip its gas, only the slow rain of hydrogen along a slender filament at the cavity's edge. It grows thin and blue, its spiral arms unruffled, its metals scarce, its rhythm of star formation measured. Another galaxy, pressed against a wall, endures steady infall and frequent encounters. It ages quickly, reddens, thickens, and perhaps feeds a lively heart at its center. Both owe their character to the same invisible ocean, one to the silence, the other to the surf. As surveys widen and deepen, the atlas of hollows becomes precise. Algorithms identify contiguous underdensities, compute effective radii, record shapes and alignments, and trace how voids cluster with other voids. Stacked lensing profiles whisper of negative mass contrast. Redshift space shapes reveal the speed of cosmic flows. The distribution of void sizes constrains the balance between matter and acceleration. By listening to the quiet between the notes, cosmology becomes more certain about the orchestra as a whole. Still, questions linger where the water is darkest. If voids are so sensitive to the properties of the unseen, what signatures would appear if the invisible were not a single species, but a chorus? If part of the dark sector exchanged energy with itself, would void rims puff differently? If quantum waves spread the unseen over kiloparsec scales, would interiors ring with interference rather than rest in calm? Perhaps the cleanest laboratory is not a blazing cluster, but a place where almost nothing happens, because small differences are not drowned by noise. There is a humility to this view that suits the hour. The universe, seen honestly, is not a contest of bright against dark. It is a conversation between fullness and the spaces that make fullness possible. Filaments cannot be understood without the caverns they border. Halos cannot be weighed without the basins that keep them apart. Dark matter writes both halves of this grammar, adding nouns and carving pauses, supplying weight and withholding it. Even silence carries information when the score is cosmic. Stand under the night and consider that most of what stretches above is not crowded at all. The Milky Way's river of light arches across a sky whose dominant feature is emptiness, structured by hands no eye can see. The same invisible ocean that opens hollows also steadies lanterns on their shores. It is one system. It is one design. And a question follows, soft as tide within a shell. If the world's most telling clues lie not in what shines, but in how the dark leaves room for shining, what secret will reveal itself when we learn to read the shapes of emptiness as fluently as we read the stars? A galaxy is more than a canvas of stars. It is a dance floor, and every star is a dancer, tracing graceful orbits around the center. For centuries, astronomers imagined those orbits obeyed the same simple laws that guide planets around the sun. Stars closer in should whirl quickly, while those far out on the edge should drift more slowly, like skaters at the rim of a rink. But when telescopes measured the speeds of stars in spiral galaxies, something astonishing appeared. The outer stars did not slow down. They raced with the same speed as those nearer to the center, as if an unseen conductor whispered to them, "All, keep the rhythm steady." These observations were first made in the 20th century, most famously by Vera Rubin and her collaborators. They traced the rotation curves of spiral galaxies, plots of orbital speed against distance from the center, and found them to be flat rather than falling. The visible matter, the shining stars and glowing gas, simply could not account for the gravity required to hold such fast orbits in place. Without something more, galaxies should fling their stars into space like sparks from a wheel. Instead, they hold together, serene and enduring. The explanation points again to the invisible. Around each galaxy lies an extended halo of dark matter, outweighing the stars and gas many times over. These halos provide the extra gravity needed to flatten the curves. They are not seen directly, but their influence is traced in every orbit, every whisper of rotation that refuses to slow. In this way, the spiral arms are like ribbons tied to an invisible frame, spinning steadily because the frame is both massive and unseen. The discovery reshaped cosmology. Before rotation curves, dark matter was a suspicion. With them, it became a necessity. Thousands of galaxies measured across the sky reveal the same pattern. Halos stretch far beyond the visible edges, embracing disks with gravity that does not fade when the light does. Even small dwarfs, with only a few million stars, reveal flat curves that betray enormous halos. The message is universal. Galaxies live in cocoons of shadow. Simulations confirm the portrait. When dark matter is included, galaxies form with extended flat curves, matching observation. Without it, disks cannot remain stable. Stars scatter, spirals wind down, and the balance collapses. The invisible halos are not accessories, they are foundations. They cradle the disks and allow their graceful arms to persist across billions of years. But mysteries hide within the details. Some galaxies show rotation curves that rise steeply and then level off. Others rise slowly, their halos less concentrated. A few, known as low-surface brightness galaxies, seem dominated by dark matter even in their centers, their faint stars tracing orbits controlled almost entirely by the unseen. Each variation tells a story about how halos form, how gas settles, how feedback stirs the mix. The flatness of the curves may be universal, but the precise shapes are signatures of history. The Milky Way's own rotation curve tells the same tale. Stars at the Sun's distance orbit at about 220 kilometers per second, far too fast for the visible mass to contain. Beyond us, out toward the disk's rim, the speeds do not diminish. They remain constant, tracing the hand of a halo that stretches far into the dark. Every time we circle the galaxy, every 230 million years, we ride inside this invisible embrace, unaware but secure. Rotation curves also provide tests of alternatives. Some have proposed that perhaps gravity itself changes at large scales, bending its rules so that halos are unnecessary. These ideas produce equations that can mimic certain curves, but when applied broadly, across galaxies of different sizes, clusters, and cosmic scales, they stumble. The simple truth remains harder to avoid. Mass unseen outweighs mass observed, and its pull is felt in every star that refuses to drift away. Still, even within that truth, there is room for nuance. Are halos smooth, or are they lumpy, filled with substructure that perturbs orbits subtly? Do they extend infinitely, or do they fade at some radius we cannot yet probe? Are they truly collisionless, or do faint interactions alter their profiles? The answers lie in careful measurements, in mapping curves to ever greater distances, in tracing the dance of stars with ever finer resolution. There is poetry in imagining these galactic ballets. A spiral galaxy, its arms glowing with young blue stars, rotates with perfect serenity, the outermost stars sweeping around in lockstep with those in the center. To see such order across such immensity is to glimpse a deeper harmony. Something vast and unseen is keeping time, like a cosmic metronome ticking beneath the music of starlight. And so, the mystery endures. We know the halos are there. We know they shape every orbit, but we do not know what they are made of. The dancers keep perfect rhythm, but the conductor remains hidden. Perhaps the more precise question is this: if galaxies move to music we cannot hear, then when we finally discover the source of that melody, what other symphonies of the cosmos will it reveal? For every mystery we have traced through these quiet explorations, one truth remains constant. Dark matter surrounds us, shapes us, defines the very architecture of the cosmos, and still refuses to tell us what it is. We have followed its whispers. In the rotation of galaxies, its shadows in the cosmic web, its fingerprints in gravitational lensing, and its echoes in the microwave background. We have seen it guide the growth of clusters, sculpt the lives of dwarfs, and carve out vast voids like an invisible ocean. We know its weight, its reach, its influence, and still, its identity is a blank space on the map of physics. This absence has become one of the great quests of modern science. Physicists imagine particles with names that sound like poetry and code: WIMPs, axions, sterile neutrinos, fuzzy fields. Each candidate promises to fill the silence, to step forward from the shadow and explain why galaxies dance the way they do. Experiments buried deep underground listen for rare collisions. Telescopes search the skies for faint gamma rays or exotic decay signatures. Colliders attempt to produce particles that slip away unseen. To this day, none has emerged, though each effort sharpens the frontier. The map expands not through discovery alone, but through knowing where the unseen refuses to be. Perhaps the answer is not a single particle, but a whole dark sector, a mirror world with its own forces, its own stories, invisible to us except through gravity. Or perhaps the answer lies not in matter at all, but in the fabric of gravity itself, a subtle rewriting of the rules we thought unbreakable. Both views have their champions, both are tested against the sky, and both continue to wait for evidence, decisive enough to end the debate. The cosmos holds its silence, and the silence is instructive. In the meantime, we trace with growing precision how the invisible sculpts the visible. Surveys map millions of galaxies, reconstructing filaments across cosmic time. Simulations run on supercomputers churn out evolving universes, showing halos, form, merge, and breathe. Instruments measure the faint shear of weak lensing, the gaps in stellar streams, the statistics of voids, the oscillations of the microwave background. Each dataset is another brushstroke in a painting that is still unfinished, still awaiting its final hues. There is something humbling in realizing how much of the universe is missing from our senses. The light of stars, the glow of gas, the flicker of quasars, all of it is the minority. Most of what is, we cannot see, and yet it shapes our lives intimately. Without dark matter, our galaxy would not hold together. Without it, stars would not cluster. Without it, the universe would be a diffuse mist without pattern, without story. Every human, every breath, every memory rests within a web of shadows. The search is not only a technical pursuit, but a philosophical one. What does it mean that we live in a universe where the majority is hidden? How should we think of ourselves, creatures of light who depend entirely on what is dark? Perhaps it reminds us that knowledge itself is a journey. Most of reality may always remain invisible, and our task is to keep listening to the echoes and watching the distortions, finding meaning in the indirect. And so this series of quiet stories reaches its close. We have walked from black holes that should not exist, to galaxies bound by ghostly halos, to rivers of gas flowing along unseen roads, to the vast silent voids where almost nothing resides. We have listened to the symphony of rotation curves, traced the fingerprints in the microwave sky, and pondered what lies beyond the arc of every lens. It has been a journey of shadows, but also of light. If you have stayed with me through these nights of exploration, I want to thank you. Your time, your curiosity, and your imagination are what give life to these quiet stories. Every listener who pauses to wonder makes the universe less lonely. Creating these journeys takes patience and heart, and your presence, your decision to listen, to reflect, to stay curious, is a true motivation. If you found meaning here, please consider subscribing or sharing these stories. It helps me continue shaping this little pocket of calm in the noisy cosmos. The universe is unfinished. Its map is drawn in part, with great oceans of shadow left, blank. But perhaps that is not a flaw. It is an invitation. As you drift tonight into sleep, let the thought accompany you. If the stars are only notes and the halos are the rhythm, then the symphony is still being written. And one day, when, The unseen reveals its name. What new harmonies will it add to the music of the universe?